Although it is important to have expressions for the chemical potential of pure substances, again, we are generally not working with pure substances. So let's look at how the chemical potential of a component in a mixture depends on composition. This will lead us to the formulation of Raoult's law. Let's look first at our liquid-liquid solution, where we can go all the way from pure A, mix in B, to a 50-50 mixture, or start with pure B and mix in A to a 50-50 mixture, so that we can have all compositions between pure A and pure B. Recall that the chemical potential of the liquid phase is equal to the chemical potential of the gas phase when this system is at equilibrium. The vapor pressure above the pure liquids depends on how strong the interactions are in the liquid phase. If there are very strong interactions, then very few molecules will be able to escape the liquid and go into the gas phase, forming a low vapor pressure. However, if the interactions in the pure liquid are weak, then lots of molecules will escape into the vapor phase, causing a high vapor pressure. It's important to understand this concept if we're going to understand what happens when we mix two liquids together to form a mixture. If the interactions between A and B are very similar to the interactions between AA molecules or BB molecules, then in the mixture, the tendency or the ability of an A molecule to escape into the gas phase has not really changed, because the interactions between AB molecules and AA molecules are about the same, or each A molecule is still held in the liquid to the same extent as it was in the pure substance. What has changed is that in this 50-50 mixture, 50% of the molecules at the surface are now B molecules. And so there will be half of the molecules in the vapor that are A and half that are B. Thus, the partial pressure of A above the mixture is half of what the vapor pressure of A was above pure A, and the partial pressure of B above the mixture is half what it was above pure B. We can summarize this mathematically by saying that the pressure of A above the mixture is equal to the pressure of A in the pure substance times the fraction of molecules that are A molecules in the mixture. Likewise, the pressure of B above the mixture is equal to the pressure of B above pure B times the fraction of molecules that are B molecules in the mixture. Or in general then, the pressure of any component I above a mixture is equal to the pressure of that component above the pure substance times the fraction of particles of that substance in the mixture. This statement is called Raoult's law and holds for substances which have similar interactions between A and B as there are between AA and BB molecules. When the interactions in the mixture are equal in strength or the same as the interactions in the pure liquids, we call this an ideal solution, and so Raoult's law holds for ideal solutions. We can use Raoult's law to write an expression for the chemical potential of each of the components in our liquid mixture. Recall that the chemical potential of a component is equal to the chemical potential in the standard state plus the correction for not being at 1 bar of pressure. So the appropriate pressure is the pressure of the gas, that component, above the mixture. Raoult's law tells us that the pressure of the component above the mixture is equal to the pressure of that component above the pure substance times the mole fraction of the component in the mixture. Making that substitution, we can write that the chemical potential of a component in a liquid-liquid mixture is equal to the chemical potential of that substance at 1 bar pressure plus RT, natural log, of the pressure above the pure substance times the mole fraction in the liquid phase divided by 1 bar pressure. We can split up our natural log term and write that the chemical potential of the component in the solution is the chemical potential in the standard state plus RT, natural log, of the vapor pressure above the pure substance divided by 1 bar plus RT times the natural log of the mole fraction of that component in the solution. Notice that the first two terms are just equal to the chemical potential of the pure liquid. And so I can write that the chemical potential of a component in a mixture is equal to the chemical potential of the pure liquid plus a correction for not being pure. And so the chemical potential of a component in a mixture depends on the mole fraction of that component in the mixture. Remember that the mole fraction is equal to the number of moles of the component divided by the total number of moles. And so it's simply just the fraction of the total mixture in terms of moles that is component I.